Hi, thanks for having me. So, first time lecturing in this room. Let's tell out a little bit more of something Anna said about the relation between Schubert varieties and matrix Schubert varieties. So I'm going to give an extremely ahistorical invention of those. So let's say I'm interested in the cohomology of the flag variety, and for fairly stupid reasons, I'm going to transpose this, and this is going to be my flag variety. So, some people have been doing row vectors, some column vectors, and they should have been doing row vectors because row vectors are just better. Typeset, for example, they're much better to typeset. Right. So this is my flag variety, and inside here I have these Schubert varieties, and so some people have been taking a Schubert variety to be B minus orbic closure, and some to take and some to taking it as a B orbit closure. The basic reason you would want to use different things on the two sides is if you're more interested in cohomology than homology. For example, if I had an infinite dimensional group here, then this guy would be finite codimensional inside that infinite dimensional flag variety. But I'm just doing GLN right now, so not an issue. This is my definition. And we're interested in, so this is a Schubert variety, and we're interested in the class of this thing, which is an element in this cohomology ring. So the way I'm going to try to get a hold of this class, in order to write it down, I might want to write down a presentation of this ring. So there is one from Burrell in the 50s. I'll get there, but I'd want to write down a presentation. So that'd be that I'd have z brackets some variables, modulo some relations. And then if I wanted to say, here's my Schubert class, in that I'd want to specify a polynomial rather than a class of polynomials. So how am I going to do that in a natural way? Let me rewrite this by thinking of it as the equivariant cohomology, or B minus equivariant cohomology of GLN. So what I'm undividing by this group, and equivariant cohomology is easy to compute in some sense when you have a free action like we have here. It's acting freely on the left of there. It's just this. So why would I want to do that? Well, a couple of reasons. So one is that there's this nice map from GLN to n by n matrices, and that map, the inclusion of this into there, is equivariant with respect to a whole lot of things like the GLN cross GLN action, but in particular with respect to this B minus action on the left. So I get a map because of that inclusion the other direction. So how do I think about this? And again, what I was really interested in was the class of this. So that's corresponding under this this definition to the class of this this closure where I'm now not divided by anything. So what's nice about this ring is, well, this is the same as, let me fix this up in a couple ways. One is that you could say it's just the equivariant cohomology of a point. And as long as I'm shrinking this guy, this big fat point, down to just a point, I'm going to shrink this big fat group down to this other group that's inside it, which it too is homotopic. And so this is where we're seeing, in a natural way, this polynomial ring in n variables. So what we have right here is this map, and we have to understand why this map is onto. We'll get there in a second. Once we know this is onto, then we'll be seeing the presentation of this ring as a quotient of a polynomial ring. I mean, this doesn't, we have to think a little bit harder to see what the kernel is, of course, of that map. All right, so back to thinking of the Schubert classes. So this guy was a subvariety of GLN, and I want to get the class of that by starting with some class on here, hopefully the class of some subvariety, that'd be nice. And the way you do that is you want to have some variety in here that when you intersect it with GLN, it should intersect it transversely, which is easy because GLN is open, so everything intersected transversely. And once we intersect, we get this. And there's a lot of options, but there's one dumbest option, which is I take this thing that I had the closure of inside GLN, and I close it further. I'm going to close it inside matrices. Okay, and this was exactly what what Fulton introduced as this matrix Schubert variety. And that is, if you take the matrix Schubert variety, you intersect with the GLN, you divide by B minus, you get the ordinary Schubert variety. And so now we have an element in this ring, so we have a polynomial. And again, there were other ways to extend this to something inside n by n matrices that would have done the job also. I could throw in random junk in the determinant zero locus, and I would get a different polynomial here that would represent the same class there. So I mean, this is not topology, this is not homotopy theory that's going on here. There's some extra geometry that's involved in saying, let's take the closure and use that as our choice of representative. Anyway, when you do that, what you get is the Schubert polynomial. So this is totally not how Schubert polynomials were invented. At the time that they were invented, combinatorialists weren't doing a whole lot of equivariant cohomology yet. That's changed over time. But this is a way of thinking about where Schubert polynomials come from. One thing I like about this, as contrasted with the original invention of Schubert polynomials, is that this isn't based on any recurrence relations. This says, if you have a Schubert class you want, then here is the thing you compute, instead of it's saying we're going to solve some big recurrence relation about here's this base case, we have to apply these divided difference operators. So it is, of course, true that these guys satisfy those recurrences, but I like having a direct thing instead of the recurrences being definition. Okay, so what are the upsides? What are good things that have happened by leaving GLN and going to matrices? So one was we got an easier cohomology ring. That it was this free ring instead of equivariant cohomology ring. This free thing instead of having some relations. So now I should emphasize this thing had a basis given by the Schubert classes. Why is it a basis? Well, we have a cell decomposition, complex cells. So they're giving us a basis for homology and cohomology. I've managed to lift every element of that basis to things in here. And so if I can hit a basis, I can hit everything. And that's why this is ought to. So that's why I am getting a presentation of this ring. But this is an easier ring to think about. I don't have to think about polynomials up to some ideal, some Borel ideal. The other thing that's, the second thing is that in terms of dealing with like varieties on a computer, it's just easier to work inside affine space. And say I've got these affine varieties. So the much cooler thing, though, is there's a much bigger group action available. So on the flag variety, if you look for a torus action on flags n, the biggest torus that can act effectively is n-1 dimensional. So it's the scalars in GLN, it's the diagonal matrices in GLN up to scalars or some conjugate of that. So here we only have this possible n-1 dimensional torus action. By the time we get to here, we have an n² dimensional torus action. So now these guys are not invariant under that n² dimensional torus, but we can use that n² dimensional torus to degenerate these. And that n² dimensional torus that's acting here contains the original n-1 dimensional torus we had. So it's if I can compute n² dimensional equivariantly in some way, then I'll be able to just forget and go down to my smaller torus and learn all the things I wanted to before. And I should say, you can, this was, as long as I'm talking about equivariant cohomology, why don't I get, equivariant from the get-go and say, these guys are defining elements in T equivariant cohomology with flag variety. So if you do that, then there's going to be a torus over here, 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 and we're going to end up with double Schubert polynomials. Okay. So let's look at a particular example of this. Here's maybe a little one would be x2413 bar. So coming back to, we've got 2 and 4 and 1 and 3. The relevant ranks here are this one and that one. The equations of this thing are that M11 and M21 are 0. So these are 0, and M12, M13, M22, M23 is 0. So the Fulton essential set was the southeast corners of the stuff that doesn't get crossed out when you're making the Roja diagram, and it got us the rank condition. This matrix is rank 0, and this 2x3 matrix is rank at most 1, and that had one more determinant involved. All right, so how are you supposed to take these equations in these polynomials? And this is a completely different polynomial ring than this polynomial ring. The relation between them, of course, is that these guys, as elements of the coordinate ring of this, they are weight vectors for that torus. So we could say things like the weight of Mij is xi minus yj. So this is the relation between these polynomials, these variables, and those variables. How am I supposed to take this thing and end up with a polynomial in x's and y's? So the idea is to degenerate this determinantal equation to just this anti-diagonal term. So I'm going to take this guy and do what I'm going to call an anti-diagonal init. So when you have so all of the equations determining this are determinants, as was in Anna's talk. And when you have a determinant, it's a sum, a k by k determinant, it's a sum of k factorial terms. And each one, so there's going to be this term and that term. And I want to always pick out the anti-diagonal term and say that's my leading term. So I'm going to end up with, in this example, M11, M21, but also M13, M22 being 0. So this thing, I started with this nice, so as Anna mentioned, Fulton proves that Fulton's determinants define a prime ideal. But once you do this anti-diagonal init, where you're picking out this leading term of these determinants, once you do that, it's not a prime ideal anymore. It breaks into pieces. So this is totally different from the reducibility that she was dealing with. I'm starting with things that are irreducible and then breaking them, whereas the things that she was getting for ASMs were reducible to begin with. So mine are irreducible to begin with, then they break as I degenerate. So how do you keep track of the pieces that this is going to degenerate into? So I'm going to put, there are 2 cases, and the way I'm going to index those cases is to put crosses at the matrix positions where there's a 0. So I'm always going to have a cross here and there. Both cases have those entries being 0, but in one case, I'm going to have a cross in the 1,3 position, the other in the 2,2 position. Okay, so I put crosses to indicate that I have some Mij equals 0 equation. Any place where I don't have a cross, I'm going to put this bump tile or elbows tile. So it's going to look like that. Okay. Okay. So, all right. So what was the input? The permutation went in. It made an ideal. We prime ideal. We degenerated that prime ideal to a monomial ideal. We took the prime components of that monomial ideal and drew these pictures. And now I'm going to follow these numbers 1, 2, 3, 4 along these pipes. And the 1's going to come out there, the 2's going to come out there, 3 is coming out at the bottom, the 4 is coming out there, and the same thing is happening with this one. Okay. So the theorem, so this is this first is going on in this paper of me and Ezra Miller in 2005. It's a few years older than that, but I got published in 2005. And what we prove in there, one of the things we prove is this statement that that the equivariant class of the matrix Schubert variety is the double Schubert polynomial. So that's pretty close to what's in Fulton's paper. Again, Fulton's paper doesn't have equivariant cohomology. He works in terms of this concept of degeneracy loci that was reinterpreted by me and independently by equivariant as doing the equivariant cohomology calculation. Anyway, so we do that, and we also follow this degeneration and see what we get. And the answer, what you get, is these pipe dreams. They should take the numbers 1, 2, 3, 4 to the permutation that we started with, right? So I got 2, 4, 1, 3, and we want to. So the rules here are crosses in the northwest triangle only, and no two pipes cross twice. So I said before that we started with only having this n-dimensional, or maybe 2n, because with the red, we got this 2n-dimensional torus acting. And then we extended it, now that we're monomial, now we have this n-squared dimensional torus acting. So we should be able to compute the classes of these guys. Sorry, and the degeneration was, you could think of it as like scaling by certain matrix coordinates, saying what happens if I scale this one big and take the limit as it goes to infinite size, and then this one, then that one, then that one. Each of these individual scalings commutes with the T cross T action, and so that's why this degeneration is T cross T equivariant. And the benefit of being T cross T equivariant is it means that the T cross T class I wanted to compute before, I could compute it after instead, but now it's a sum. So this guy is going to be getting me the factor of x1 minus y1 times x2 minus y1 for those two, times x1 minus y3 for that guy. This one, instead, it's going to get a x2 minus y2. So there's the double Schubert polynomial for 2413 as this sum over these pipe dreams. So again, very ahistorical. The pipe dreams were invented in '93, and they were invented to compute the single Schubert polynomials, but there was no geometric understanding of them at that time. There was just, we've done a bunch of combinatorics with Schubert polynomials, and Bergeron and Billy and Sergei and Anatol Kirillov come up with these pictures to reinterpret this sum over reduced compatible sequences formula that had come shortly before for the Schubert polynomials.
Sorry, what does it mean geometrically for pipes to cross twice?
So if you can wonder, now that I have, okay, so one of the things that was interesting about this picture that had not been present in, say, in the previous pipe dream papers, is since these are these coordinate spaces, you can think not just about what are the coordinate spaces, what are the components of my degenerate thing, but how do those coordinate spaces intersect one another. So if I look at this guy intersecting that guy, that's like saying I want to have these be 0 and those be 0, so all four things be 0. And then I would have a cross here and again across there. So the pipes crossing twice has to do with looking at the glue between different components. And so that's relevant if you wanted to compute not the cohomology class of this thing, but the K class. Because the K class of this would be the class of this plus the class of this minus the class of the intersection. And so then I'd want to I want to have a formula be a sum over pipe dreams that would allow double crossings in certain situations and introduce signs to handle the inclusion exclusion. All right. So that's story number one. Story number two begins here. So let's think about, instead of northwest rank conditions. So remember, this guy was defined by the northwest 2 by 1 is rank 0. The northwest 2 by 3 is rank 1. And for every northwest I by j, I could have measured the ranks and would have gotten a whole rank matrix. So I want to do something like that. But instead of thinking about northwest rank conditions, so say, instead of northwest rank conditions, look at interval rank conditions. So the idea is I'm going to have some matrix, some k by n matrix, and I'm going to look at intervals in it and intervals of columns. And I'm going to ask for what's the rank of this interval. So for every interval of columns, I can associate the rank. And if you go to a larger interval to the left or larger interval to the right, but if you expand your interval, then the rank could stay the same or it could go up by 1. And but if, like, when you go to the left, it doesn't go up, and you go to the right, it doesn't go up, then doing both of them, it's still not going to go up because neither one of them has given you a vector that wasn't in your span. So you end up with this forbidden possibility that corresponds eventually to now it's the analog of I don't want ASMs, I want permutation matrices. So what's actually going to be more fun than intervals is to look at cyclic interval rank conditions. So let's say, the way I'm going to think about that is that I'll copy M. So I'll have these copies of M, infinite future, infinite past, and not only will I consider intervals in M, but I'll consider intervals that wrap around and use the end of M and then come back at the beginning of M. Okay, so how do I encode that? Before we encoded the intervals, we encoded the ranks with this northwest, with this rank matrix, and then said, well, the rank matrix is the same data as a permutation matrix. And so to be clear where I'm getting permutations and not ASMs. So if I start with a actual matrix, if I start with some matrix full of numbers, and I measure the ranks to the northwest, I will get a rank matrix for a permutation, not for an ASM. So that's the sort of picture I'm thinking of. I'm going to imagine there's some actual M, I measure the ranks of all cyclic intervals. And because this guy has this n-fold periodicity, when I measure the rank from I to j, it's the same as for n plus I to n plus j, and so on. So there's not infinitely many different numbers to consider here. At some point I'm going to tap out, I'll see the entire M, and it's got whatever rank it has, and that's going to be the biggest number I ever see. All right. So I want a recipe where a matrix goes in and some combinatorial object comes out, something like a permutation matrix, that encodes the data of all those ranks. So here's the way I want to do that. Let's think of M as being a bunch of column vectors, which is kind of funny because the rank conditions are invariant under row operations, but bear with me, I want to do column vectors. So I've got these column vectors, and Vn plus 1 is the same as V1, and V0 is the same as Vn, and so on. And associated to this, so associated by a matrix, I'm going to make a function from Z to Z. And the function is f of I is defined to be the smallest j more than I, such that column I is in the span of the columns that came after it, only needing to go as far as j. So I take some column and I say, how far out do I need to look before that guy's in the span of the stuff that comes in the future? So two extremes. If my column is 0, then I don't need anything. It's in the span of the empty set. And so in that case, j would be I because it has to be at least I, right? So one thing that's clear here is whatever this f of I is going to be, it's going to be at least I. But it's also going to be at most n plus I, because even if I have some column that's independent of all the other columns, it's not independent of itself, right? So, so that's as far out as I'm going to need to look. So there's only, in particular, there's only finite. Oh, the other thing that's really obvious here is when you start n steps later, you end up n steps later. Okay. And so what's actually going to be nicest to write down for such a thing is the list f of 1 minus 1, f of n minus n. So it's just say, once you know those n numbers, and each of these is in this range from 0 to n. Once you know those, then that's going to repeat periodically because of this. Okay, so there's one other property that maybe there's two other properties to say that these f's must have. So this was my definition, where matrix goes in, the f's come out, and this was some properties of f. Okay. So there's a couple other properties that this f must have. One is that f is bijective. And so that's a fun linear algebra thing to figure out why it's injective. And once it's injective and it has this periodicity, that's enough finiteness to make it bijective. And another is that the average of this guy, f of I minus I, is k, well, or is more honestly, the rank of f. So that turns out to be all the conditions on f. Every f that does these things does actually arise this way. Okay, so what's the best way to interpret such an f? Everybody knows the answer. Yes?
Juggling pattern.
It's a juggling pattern. Right. So let's do an example. Okay. So let's take a matrix. How about this 4x6 matrix? So a pretty simple one. E1, E2, E3, E3, E4, E4 in this 4x6 matrix. So I want to take this matrix and read off these numbers. So the question is, how far in the future do I need to take this vector before it's in the span of the vectors ahead? And the answer is, this guy, it's not useful to see any of these. You're going to have to wait until you come out there. So that's 6 steps later. Okay. And this guy's same boat. It's going to take 6 steps before that guy's in the span of itself. This one is in the span of the very next one. So 1 step later. This one is going to be in the span of that one, repeated the next time around. And this is the same story. So the average there of these numbers is 4. And so this is a 4-ball pattern. So what does it look like? This is, mathematically, you could say we're doing one-handed juggling here, but one tends to interpret this as two-handed juggling, that we're just going to do in even times, I'll throw with my right hand, odd times, I'll throw with my left hand. So once you have that interpretation, that's going to force, whenever you do one of these even throws, it's going to go from a hand back to itself. Whereas these odd throws are going to go from a hand to another hand. So what's going on with like these 1-5s? So if I just had if I just had 1s and 5s, that would mean from my right hand, I would just be doing 5s. And from my left hand, I'd just be doing 1s. And altogether, it'd be these 5s and 1s. So the average of 5 and 1 is 3. So this is this pattern, 5, 1, 5, 1, 5, 1, 5, 1, 5, 1. And so 5, 1 being even length, it's it keeps repeating. There's always my right hand, there's always my left hand. So these 6s, though, are going to be doing this 6, 6 stuff. And so I'll have this happening on the sides, and then the 1, 5, 1, 5 happening in the middle. And all together. Got the 6s on the sides, and the 1, 5, 1, 5 in the middle. All right. Find me after the lightning talks. if you already know how to juggle, but you want to the next trick, or if you don't know how to juggle. All right, so great. We have this recipe where matrices go in, and you could say matrices up to row operations, right? Because if I do a row operation here, that's not going to change these spanning conditions. So this is really giving me some map from Kn to K ball patterns. K ball juggling patterns. And there's this weird thing of like periodicity n. But there's this weird thing about the patterns from the juggler's point of view, which is this condition. So the first pattern you might think of would be that n is 1 and f of I equals I plus 3. So that's, while one volley's in the air, I do two other throws. Every throw is going to be the third throw again, after it comes down. So this is a period 1 pattern where all the throws are 3s, which is to say it's violating this bound. So this is a very strange condition from the juggler point of view, but it's showing up naturally if you from the Grossmanian. Okay. So now you can ask the question. Sure. So given f, what is, and let's define pi f to be the space of elements of the Grossmanian. So V is the row span of some matrix, and I want the associated juggling pattern is this guy F. And so with this bijective, you think we should be able to describe this in more group theoretic terms. And so if I included this condition and this condition on F, I just have functions from Z to Z, they're permutations, and once they do this, then they're called affine permutations of periodicity n. So we're dealing with affine permutations with these two bounded conditions. And associated, so that's what you should think of F to be if you don't like Richard's answer. It's an affine permutation with these two weird boundedness conditions and this average condition. So I should say the group of affine permutations is not a Coxeter group. Inside the group affine permutations, there's the affine permutations where this average is 0. So that's really boring if the thing is also bounded, that it's the zero ball juggling pattern. It's just the identity permutation where you sit there with your hands empty. Okay. But if you allow for, if you leak in this, then you can have balls going backwards in time. And there's this really excellent video called Negative Site Swaps that demonstrates what those look like. Yeah, this thing here is called the site swap. All right, so question. I got this F, it's this affine permutation or it's juggling pattern. I've got these guys pi F, which is some subset of the Grossmanian. And like Schubert variety, I want to take this closure here. And I've got now pi F is some element in the cohomology of the Grossmanian. And there's a map to there from the ring of symmetric functions. And one can ask, what's a representative for this class? And so theorem, me and Thomas Lamb and David Spire in 2013 is the affine Stanley symmetric functions. Here, yes, I want to say affine Stanley sub F is such a representative. Now, once again, this is there's something special going on here because there's many different things that could represent the same class. So just like back here, there were lots of options. And I should say, you may think, well, obviously this is the right option. So actually there's this paper, Bernstein-Dilfan from '73 that also gives representatives for Schubert classes and does not use Schubert polynomials. Uses a, in some ways, more natural choice that works for arbitrary groups, not just GLN, and doesn't satisfy the same stability condition that Lescu and Schutzenberger used to characterize and invent Schubert polynomials. So really, there really are choices going on here, and ever so much more here. So we came up with these Thomas had already invented them for some other reason, but recognized that they could serve as representatives for the positroid classes. But like, here's a sense in just how weird this question is, and these are as representatives. These are not sure positive. Okay, so if I have any variety in the Grossmannian, it's going to expand, its class is going to expand positively in the, let me call them sure classes on the Grossmannian, Schubert classes, but they're usually represented by sure functions. So by the time you take an affine Stanley here that's not sure positive, and you map it into there, a lot of the parts of it will have mapped to 0, and all the ones with negative coefficients will be gone. You'll just get the positive ones. So it's kind of a hint that just how weird this was as a choice. But anyway, that's something true. So what's new? Last year, there's this paper by Fan, Guo, Su, and Xiong, where they give a, so I'm going to give a very lame and tiny bit of what they did to begin with. So I'm saying that in advance so that because what I'm about to say won't sound as impressive as what they actually did. I'll get more to what they actually did soon. But one thing they do is they give a pipe dream formula for the affine Stanleys. So what it looks like is it's going to be pipe dreams inside a k by n rectangle. So it's still going to have crosses and bumps. And it should be periodic. So it's actually, so let me stick that word in there now, actually. So they introduce this concept of periodic pipe dreams. There was a similar concept in Michelle Snyder's thesis that I'm not going to get into. But you should think of this periodically, and particularly because if you start here and try to follow a pipe, then it might come off this side and come back on that side and come up to somewhere. So before we were connecting the numbers one through n on one side to our permutation on the other side. And we're going to be doing that here as well. That we're going to be connecting 1 up to n here with f of 1, f of n there. Okay. So if and we'll do a couple of examples of this in a moment. Maybe I'll do that right now. What if we had, for example, so the theorem is going to be that you fix your f and you sum over these periodic pipe dreams that, again, they only use these and no two pipes cross twice, and each one of them contributes a product of xi minus yj's based on where the crosses are. You add those up and you get xi minus yj. All this stuff can be done T equivariantly. And you get a polynomial in x's and y's that then represents the class of positroid variety. So let's do a funny example. Let's take K and N to be 2, and let's take F to be the site swap. So as a site swap, it's going to be 1, 1. So this is the juggling pattern. See, the average of 1, 1 is 1. So it's a 1-ball pattern, and it looks like this. Okay, so all its rows are 1s. So it's my left hand is doing the same thing as it was doing in here, but then my right hand is doing that well. So what do the pipe dreams look like for this? Yeah, the periodic pipe dreams. So I want to have 1, 2 here and 2, 3 there, because this is really I is going to I plus 1. And so there's 2 options. I could have crosses up there and then bumps there, or I could have crosses down here and bumps there. Here are the 2 periodic pipe dreams for this case. Now this case might look kind of stupid because we're thinking about the Grösslanian of 2 planes and 2 space. So maybe not that interesting a case.
Right, so to get a labeling, I'm reading in mod n. 3 and 1.
No, so when I go from here, I'll have n plus 1, n plus 2, and here is 0, -1, and so on. So this infinite thing, so the tiles are repeating, but the numbers are not repeating, right? Over here, I'm getting f of n plus 1, which you'll remember was f of 1 plus n.
Okay.
So eventually I'm getting the integers in order on the top and the integers twisted by f on the bottom. And and they're connected by, you follow the pipe and got it. Okay, so what Paul Zinn-Justin, my co-author on the stuff I'm about to tell you about, and I were interested in was the actual formula that's going on here. So remember, back in this story, the double Schubert polynomials have been around, I don't know, 25 years or so, by the time that Ezra and I said, well, not as long. They've been around, I guess, 15 years or so before Fulton interpreted them in terms of these degeneracy loci, and then a little bit longer before we said, oh, they're actually these equivariant cohomology classes. But in particular, we said it's not just the class, not just their image inside this quotient ring that's of interest. Already upstairs, this thing itself is of interest to it has meaning as it's the class of this major Schubert variety, and the formula itself, the pipe dream formula, also has geometric meaning. But with this degeneration. So here, their theorem is if you want to understand this class over there, you can get it by doing this sum over these pipe dreams and then mapping it here and getting this class. And we wanted to understand what is this actually the class of somehow upstairs. So the naive thing, okay, so the naive definition of matrix positroid variety is we've got the Grösslanian, and we have a map to there from rank K, K by N matrices. And that map is you divide by the left action of GLK, or you might call it row span. And then that thing lives inside all K by N matrices. And so fine, you take your positroid variety here, you lift it up to its preimage there, you take that thing here and take the closure, and that will get you something that will get you a variety here whose class will compute the class here. But that turns out to be bad. That turns out to not be the right thing. And So it's wrong. So there's a hint already that something subtle is happening in this example. So in this example, this 1, if we go back to thinking about what 1 means, right? 1 means that your column is dependent on the next column, that those 2 columns are linearly dependent. So here, I'd be saying my first 2 columns are dependent, and then my second and third column are also dependent. And those are supposed to be 2 different statements, but obviously they're the same statement. So instead, we pick a generic diagonal matrix theta, K by K matrix. And look at interval ranks. And so I'm going to take this guy M, and instead of copying it infinitely many times like I was doing there, I'm going to do that, but with thetas. So I'll have theta times M, theta squared times M, and coming back the other direction, I'll have theta inverse times M, and so on. So again, I have a K by infinity matrix, and I'm again measuring ranks of intervals in this K by infinity matrix. And it's again the case that if I measure the rank from I to J, it's the same as measuring it from N plus I to N plus J. But it's no longer true that, in particular in this example, it's no longer true now that I'm going to have V1 and V2, and then copied over theta V1, theta V2, and so on. This dependency condition is not the same as this dependency condition. So in fact, what's happening in this example, if theta is generic, for V1 to be linearly independent with theta V1, that means that, and theta was generic diagonal, the 2 diagonal entries are different. That means that V1 has to either be E1 or E2. And similarly with V2, but actually it's got to be the same multiple. So it has to be a multiple of E1 or multiple of E2, and V2 likewise. And that's what we saw here. This was the case. This was coming from the matrix that looks like 0, 0, AB, was getting us that pipe dream. Here we have zeros on the bottom, getting us this pipe dream. So you impose these 2 conditions, this one and that one, and the resulting scheme is reducible. It had these 2 choose one many pieces. Yeah.
Want to scale the columns so that it makes the best act on the right. I think.
Correct.
You have it as.
And therefore, I don't want to scale the columns. Scaling the columns is dumb. V1 is a column vector, and I'm left multiplying that column vector by my 2 by 2 matrix.
That scales the rows.
Of V1. It scales the two 1 element, yes. Yep.
Why don't you allow one of the vectors to be 0?
So if I did, then I wouldn't get this site swap, right? I would get a 0.
Okay.
Okay. So then our theorem is some theorems here of me and Paul Zinn-Justin are, let's see, these matrix positroid varieties are smooth. I mean the open ones where you impose certain rank conditions and with equality and not inequality. So the closures, of course, are going to be like the singularities like Schubert varieties have, which are singular but under some level of control. And irreducible if the average of f of I minus I is the size of your matrix. So that wasn't true here, where the average was 1, not 2. And I ended up with this reducible thing. And when you take the class of this matrix positroid variety of F, then that's going to be the sum over the periodic pipe dreams. So that's what these 4 authors were computing. They're computing the classes of these slightly subtle definition of periodic pipe dream. All right, so I've got only a couple of minutes. 20 minutes?
I mean, technically it's in, but we have 7 minutes now for questions, so I think we should.
All right, well, I will use one more then. So I promised you that they did something cooler. And so what they did, they computed not only the fundamental classes of these things, but actually the Chern, Schwartz, MacPherson classes of the open matrix positroid varieties. Well, excuse me, they're thinking about just the positroid varieties, and they said, here's a formula for the CSM classes of the positroid varieties. So what happens in the CSM formula is pipes are allowed to cross twice. And if they do, you just let them. So if you've run into this K-theoretic thing, Gröbner stuff, where when pipes cross a second time, you pretend they didn't. No, here we're saying just follow the pipes. They do what they do. They cross twice. That's fine. Then they said that gets you a polynomial that computes the Chern, Schwartz, MacPherson class. And so we do that then with the matrix positroid varieties and say some of these periodic pipe dreams. And let's put in this word generic here to allow for the possibility that pipes cross twice. All right.
All right, any questions for Alan?
So there's an embedding of like n by n matrices in GRn comma 2n, where you like stick an identity matrix.
Yeah.
To the left, does that make any sense? Here?
So the basic thing that's bad about that trick for these things, and it doesn't have anything to do really with this theta stuff. You could have asked that already in the positroid varieties. Is the basic thing that's bad is these intervals that go past the end and come back at the beginning. And now they're going to do that, and they're going to go through this identity matrix that you stuck there. So there's a subcase of positroid varieties, which I called interval positroid varieties, meaning not cyclic interval positroid varieties, and they behave in this stable way. So they are the ones that are sort of naturally good for this construction where you're not. And then like they're easier in a whole bunch of ways. I gave a positive formula. So we don't have any positive formula for this. I should say this question is 100% equivalent to the Schur times Schubert question. And we don't have a positive formula for that kind of Schubert calculus. But for the subcase of the interval positroid varieties, we do. I gave like 12 or so. And also, you can represent those classes with ordinary Stanleys, you don't need affine Stanleys. And ordinary Stanleys are sure possible. Yeah.
Your matrix Schubert story involved an like taking antidiagonal initial ideals. Do you want to do that over here?
Yes.
Okay. Yeah.
So there's two things about this. So yeah, you can do there is a degeneration. So we do give a degeneration. What's trickier is we actually, in order to do the CSM story, everything's been kind of doubled. It doesn't really live inside matrix space, but inside the cotangent bundle to matrix space. And so when we do the degeneration there, it all works. We degenerate to a scheme with one component for each of these generic periodic pipe dreams. But those individual components are not coordinate spaces. They're pretty easy. They're quadratic complete intersections, but it's not as easy as in the non-CSM story. But here's the CSM story.
If you like non-naive matrix positroid varieties, what happens when you kind of do the same? If you kind of go back through that sequence path, if you send it down to the grass mapping.
It's a bit tricky because these guys are no longer GLK invariant because of the theta. Okay, so so you can't quite do that. So it does mean if one can compute the class of these things, what does that have to do with the class the positroid variety? Why is it the same at this generic theta as what we were doing before when theta was the identity? And it's not obviously the same. And what we do in the paper is say, well, as your theta degenerates to being the identity, then you pick up the thing you would expect, the naive answer, possibly union extra junk that's along the lower rank part of your matrices, which then disappears when you go to the Grossmanian. So it's pretty pretty sketchy territory, but yeah, it's not obviously related because of that failure of the GLK invariance. I mean, you can of course build. Well, yeah.
All right, there are no further questions. Let's thank everyone.